Hello, dear programming and technology enthusiasts. Welcome to an exciting journey into the world of the C programming language, where we'll explore step by step how to program touch sensors for a surgical robot performing a precise operation, like removing a brain tumor. This will be a story filled with details presented in a simple, engaging, and easy to listen to way, as if we're sitting together over tea, chatting about the future of medicine. Our goal is to create code that's not only functional but also clear, and to make the whole experience smooth and pleasant even when read by a speech synthesizer. Ready? Let's dive into the world of robotics, microcontrollers, and C programming. Picture an operating room of the future. At its center stands a surgical robot like a mechanical artist, moving with watchmaker-like precision through the delicate environment of the human brain. Its arms, equipped with surgical tools, are fitted with touch sensors, small, clever devices that act like a surgeon's sense of touch. These sensors detect pressure, tissue texture, and the boundaries of a tumor, helping the robot distinguish healthy tissue from what needs to be removed. Our job is to write a program in the C language that enables the robot to read data from these sensors, analyze it in a fraction of a second, and make decisions like stopping its arm to avoid damaging healthy tissue. It sounds like a challenge, but C, a simple yet powerful language, is the perfect tool for this task. It's like a conductor's baton, giving us precise control over every part of the system. Let's start by understanding what touch sensors are. Think of them as highly sensitive fingertips, but instead of skin, they're made of electronics. These sensors can work in several ways. Some called resistive sensors measure changes in electrical resistance when pressed, like squeezing a softball and feeling how its firmness changes. Others, capacitive sensors, respond to changes in an electric field, similar to the touch screen on your smartphone that knows where your finger is. Then there are piezoelectric sensors, which generate tiny electrical pulses when pressure is applied, like miniature power plants reacting to force. In our robot, these sensors are mounted on the tips of the surgical arms, which move through the brain with millimeter precision. When the robot touches tissue, the sensor sends a signal to a microcontroller, a tiny computer that serves as the system's brain. The microcontroller processes these signals and decides what to do: continue moving, slow down, or stop. Our goal is to write a C program that handles these sensors in real time. Think of it like a recipe for your favorite dish. Every step needs to be precise, but the process should be enjoyable and straightforward. We begin by setting up the microcontroller, our little computer inside the robot. This is like preparing your kitchen before cooking. Everything needs to be in place. In C, we write a function that configures the microcontroller's ports to communicate with the sensor. Imagine telling the microcontroller, hey, this specific pin on your board is connected to the touch sensor, so get ready to receive signals. We also set how fast the microcontroller should read data, like choosing the right speed for a mixer to get the perfect batter consistency. Since touch sensors often send analog signals like a continuous wave, we use an analog pin on the microcontroller, which has a built-in analog to digital converter to turn those waves into numbers we can work with. Next, we move to reading data from the sensor. Picture the sensor sending a signal that indicates how much pressure it's detecting. For example, a light touch might be a value of 20, while a strong press, like hitting the tumor's edge, could jump to 100. In C, we write a function that tells the microcontroller, check what the sensor is saying and store it as a number. This function starts the analog to digital converter, waits for the result, and saves it in memory. It's like asking an assistant to check a thermometer and tell you the temperature. In a real system, we'd also need to ensure the data is clean. Sensors can pick up noise like static on a radio. We could add simple filtering, like averaging multiple readings, to make sure the data is reliable. Now it's time to analyze the data. This is the critical moment, as the robot needs to understand what the sensor's numbers mean. Imagine a surgeon looking at test results and saying, aha, this is different from healthy tissue. In our program, we set a threshold. Say, if the pressure exceeds 50, it means the robot has reached harder tissue, like a tumor. we write code that compares the sensor's value to this threshold and makes a decision. If the pressure is too high, the robot should stop to avoid damaging healthy tissue. It's like programming an instinct. The robot feels a change and reacts instantly. In C, we use simple conditions. If the value is above the threshold, we set a flag that says tumor detected. This flag acts like a signal to the rest of the system that something has changed. The next step is controlling the robot based on this data. If the pressure is below the threshold, the robot can keep working, moving its arm with precision. But if the pressure is too high, it stops the arm's motor to prevent a mistake. We could also add a warning signal, like sending a message to the surgeon's console or lighting up an indicator. In C, we write an instruction that says if the tumor detection flag is active, turn off the motor and signal it. It's like telling a driver, slow down, the road's slippery. In a real system, we might also include actions like gently retracting the arm or adjusting its path to avoid obstacles. But for our lesson, we keep it simple, like toggling a light to indicate detection. The final piece is ensuring the program runs in real time. A surgical robot can't afford delays. It's like a heartbeat that must keep a steady rhythm. In C, we write a main loop that constantly checks the sensor, analyzes data, and controls the robot. This loop is the program's heart, like a metronome for a musician, keeping everything on track. We also need to ensure the loop is fast and doesn't overload the microcontroller. In real systems, we often use interrupts like an alarm clock that tells the microcontroller time to check the sensor. This makes the program more efficient by avoiding unnecessary waiting. Let's dive into some technical details to make this clearer. The microcontroller we're using could be a common AVR chip like those in Arduino boards, or a more advanced ARM Cortex often found in medical systems. The touch sensor is connected to an analog pin linked to the analog to digital converter, which turns the sensor signal into a 10-bit number, giving us values from 0 to 1023. This range is precise enough to distinguish a light touch from a firm press. In our program, we configure the converter by selecting the right channel, setting a reference voltage, and choosing the conversion speed. It's like tuning a camera to take sharp photos in the right lighting. Another key aspect is error handling. Sensors can give false readings due to electrical interference or environmental changes, like a thermometer jumping if someone bumps it. In C, we can add checks to ensure the data makes sense, like verifying the reading is within a reasonable range or doesn't spike unnaturally. We could also store the data in memory for later analysis, like a flight recorder in an airplane. In a medical system, we'd need to comply with standards like ISO 13485, which sets rules for medical devices. This means the code must be tested thousands of times to ensure it never fails at a critical moment. For controlling the robot, we use a digital output pin to signal actions like turning a motor on or off. In a real surgical robot, multiple motors control different axes of movement, so our code would interact with a complex motion control system, possibly using kinematics algorithms to calculate arm movements in three-dimensional space. For our lesson, we simplified this to a single output, like lighting an LED to signal tumor detection, a small step toward a real system that you could test on basic hardware like Arduino. Speaking of testing, if you want to try this yourself, grab a microcontroller like an Arduino Uno and connect a simple touch sensor, such as a variable resistor or a TTP23 capacitive module. Write a C program to read the sensor and light an LED when the pressure exceeds a threshold. It's like building a mini version of our surgical robot. You could even connect multiple sensors to simulate a full operating area, creating a map of tissue types. This is a great way to see your code come to life on real hardware, and you can do it purely in C, avoiding the C++ libraries Arduino often uses. Why does this matter? Programming touch sensors for a surgical robot isn't just a technical challenge, it's a way to make technology save lives. Every line of code we write is a step toward operations that are safer and more precise than ever before. C is perfect for this because it's fast, gives full control over hardware, and lets us write code that reacts in milliseconds. But this is just the start. In a real system, our code would be one piece of a larger puzzle, including mechanics, electronics, and user interfaces for the surgeon. We'd need to add features like serial communication to send data to the surgeon's console or handle multiple sensors for a 3D tissue map. We could even explore machine learning to help the robot better recognize tissue types. I hope this lesson has inspired you to experiment with C programming and shown you the incredible impact code can have on medicine. It's like building a bridge between technology and human lives. Every detail counts. Try writing a simple program on Arduino to simulate a touch sensor, or think about adding features like data logging or error handling. In future lessons, we could explore further, like how the robot communicates with other devices or how to optimize code for even faster performance. Let me know if you want to try it out or have questions. The world of C programming awaits, and the future of medical robotics is in your hands. See you at the next lesson where technology and passion meet again.